Every year, more than 60 million tons of soap are produced, a figure large enough to turn this seemingly simple item into the symbol of a massive industry. Few people realize that one of the core ingredients behind those clean, fragrant bars of soap is sunflower oil, the familiar liquid gold found in every family kitchen. From sun-drenched fields, millions of tons of dark seeds are harvested, transported to factories, and put through a series of processing stages on modern production lines to become sunflower oil before ultimately reaching consumers in the form of soap. Today, join Agriculture Insight in exploring the soap industry and witness how humans transform natural ingredients into a symbol of cleanliness and vitality. It all begins right now. More than 4,000 years ago, in ancient Mesopotamia, humans accidentally created one of the most influential inventions in history: soap. By boiling animal fat with wood ash, they discovered a compound capable of washing away dirt, laying the foundation for the concept of hygiene, a core element of modern medicine. From the Roman civilization to the Arab world, that early formula continued to be refined with the addition of plant oils, gradually entering the industrial era in Europe. For thousands of years, soap has quietly served as a protective shield against disease, a simple yet enduring invention that has accompanied the development of clean and progressive civilizations. Now imagine just a single day without soap. Within only a few hours, countless bacteria could cling to the skin without us even noticing. Soap is what prevents that scenario. When mixed with water, its molecules break down the lipid membranes surrounding bacteria and viruses, causing them to disintegrate and be washed away. This seemingly simple chemical mechanism has helped save billions of lives, from 19th century cholera outbreaks to modern-day flu pandemics. Therefore, soap is not merely a common cleaning product, but the most fundamental and essential line of defense humanity has against the invisible microbial world. The journey of soap production begins in vast sunflower fields bathed in sunlight, where each blossom turns in rhythm with the sun's path to nourish the seeds within. This is the first stage and also the most crucial foundation of the entire process, as the quality of the harvested seeds determines the efficiency of oil extraction as well as the saponification reaction later on. Although soap can be produced from many different fats such as animal fat, coconut oil, olive oil, or palm oil, sunflower oil is increasingly favored for its sustainability and environmental friendliness. Sunflowers thrive in warm climates, require about 2,000 hours of sunlight per year, and use very little agricultural chemicals, thereby minimizing negative environmental impact. The harvest season begins when the sunflower heads droop, the back of the flower turns brown, and the seeds inside reach natural dryness. Farmers use handheld moisture meters to check each batch of seeds, harvesting only when moisture content falls below 20% to prevent shell cracking and reduce oil loss. Harvesters are equipped with narrow cutting heads adjusted to the height of the flowers to cut only the heads without damaging the stalks. Inside the machine, a rotating drum gently separates the seeds from the flower head, while a fan blows away petals and large debris. Parameters such as drum speed and airflow pressure are continuously monitored to minimize shell breakage, a key factor in preserving oil quality. After separation, the seeds are collected into well-ventilated containers to prevent moisture condensation and maintain natural dryness. At the end of the day, each batch is quickly tested for moisture and impurities before being transported to the nearest receiving station, officially entering the post-harvest processing stage. Immediately after leaving the fields, trucks loaded with sunflower seeds arrive at the receiving station to begin the post-harvest processing stage. This is an extremely important step to stabilize the quality of the raw materials before oil extraction, as freshly harvested seeds still contain impurities and high moisture levels, which can lead to spoilage if not handled promptly. In the intake area, the seeds are poured into receiving hoppers and then passed through a multi-layer vibrating sieve system. Each sieve layer has different mesh sizes to remove straw, dust, shell fragments, and empty seeds. At the same time, high-capacity fans blow air in the opposite direction of the falling seed flow, carrying away lighter impurities. Only seed batches that meet the required size and weight standards are transferred to the drying stage. The drying process is carried out using continuously circulating hot air, maintained at 100 to 110 degrees Fahrenheit for several hours to reduce the seed moisture content to approximately 8 to 10%. The temperature must be strictly controlled. If too high, the fatty acid structure may be damaged. If too low, the seeds remain moist and create conditions for mold growth. Temperature and humidity sensors are installed throughout the drying chamber, continuously transmitting data to the central control panel for engineers to monitor in real time. Once the standard dryness level is achieved, the seeds are naturally cooled, then pass through a metal separator and a final sorting system to completely remove any remaining impurities. Finally, the clean, dry, and uniform sunflower seeds are stored in sealed steel silos, ready for the oil extraction stage. The moment they are transformed into a stream of golden oil, the precursor to future bars of soap. When the seeds reach their ideal moisture level, they are transferred to the oil extraction area, where the valuable essence inside is extracted under extremely high mechanical pressure. First, the seeds are crushed by a dual steel screw system, breaking their structure into thin fragments to increase extraction efficiency. The crushed material is then fed into a screw press, where compressive force can reach thousands of pounds per square inch, pressing the oil out through ultrafine filtration gaps. The liquid obtained is known as crude oil, while the remaining press cake is reused as animal feed or converted into biofuel. At this stage, the crude oil is dark yellow and still contains natural impurities such as waxes, proteins, and mechanical residues. To stabilize quality, the oil is gently heated to approximately 160 to 180 degrees Fahrenheit to remove moisture, then filtered through cellulose membranes or filter aids to eliminate solid particles. In modern facilities, the oil also undergoes a cold dewaxing process. The temperature is lowered to about 35 to 40 degrees Fahrenheit so that waxes crystallize and can be separated by centrifugation. After refining, the oil becomes clear, light yellow in color, with moisture below 0.1% and a low acid value, meeting standards for food and cosmetic use. Before storage, random samples are tested for purity, peroxide value, and oxidative stability to ensure long-term consistency. The finished oil is then stored in airtight stainless steel tanks, protected from light and oxygen, ready to enter the next stages of the production line. The refined sunflower oil is then pumped into the reaction vessel, the heart of the entire production line, where the most critical stage takes place, the saponification reaction. This is the chemical reaction between vegetable oil and a strong alkali, typically sodium hydroxide NaOH, producing two main products: soap, the sodium salts of fatty acids, and glycerin, a natural humectant that helps keep the soap bar soft and gentle on the skin. Thanks to its high content of oleic acid and linoleic acid, sunflower oil allows the reaction to proceed steadily, resulting in fine lather and a light texture. The oil is heated to approximately 140 to 160 degrees Fahrenheit before the NaOH solution is introduced under carefully controlled pressure. A twin helix agitator system operates continuously to ensure thorough mixing of the oil and alkali molecules. Sensors continuously monitor pH, temperature, and electrical conductivity to prevent excess alkali, a factor that could cause skin irritation. As the reaction nears completion, the mixture begins to thicken and changes color from pale yellow to creamy white or light brown, depending on the type of oil used. In the final mixing stage, natural pigments such as clay, activated charcoal, or turmeric powder are added to color the product while the soap mass remains warm. The crude soap is then separated from the glycerin solution and washed with brine to remove impurities before being transferred to the neutralization area. Although this process originates from techniques developed thousands of years ago, precise control of temperature, timing, and reaction ratios remains decisive in producing high-quality sunflower oil soap, smooth, mild, and safe for the skin. After neutralization, the crude soap is cooled and then ground into small pellets, known as soap noodles. These pellets are fed into a twin-screw mixer, where two counter-rotating shafts continuously knead the material to create a pliable, uniform texture. During this process, glycerin is added to maintain natural moisture, purified salt increases hardness, and natural essential oils such as lavender, bergamot, orange, or peppermint are sprayed directly into the mixing chamber to create distinctive fragrances. If color is desired, natural mineral pigments such as red clay or activated charcoal are incorporated at the final stage. All parameters, including temperature, viscosity, and mixing time, are strictly controlled to ensure that fragrance and color are evenly distributed throughout the entire soap mass. The result is a smooth, soft soap base with stable structure, ready for the subsequent shaping stages. After the blending process is complete, the smooth and pliable soap mass is transferred to a vacuum plotter, a machine responsible for compressing, deaerating, and homogenizing the material before shaping. Inside the extrusion chamber, a rotating screw continuously pushes the soap forward under high pressure. In the middle section of the machine, a vacuum chamber operates to completely remove microscopic air bubbles and trapped air pockets within the mixture, ensuring that the extruded soap becomes dense, solid, and perfectly smooth on the surface. Once stable pressure is achieved, the soap is forced through a steel die fitted with dozens of small concentric round openings. Under strong compression, the material is extruded into soft, uniformly colored strands, an indication that plasticity and moisture content have reached ideal levels. These strands are continuously collected on a conveyor belt, gently cooled and prepared for milling or a second extrusion to further increase density and uniformity. The vacuum extrusion stage not only provides the soap's initial form, but also determines the product's physical integrity. If pressure or vacuum levels are not precisely controlled, the finished bars may develop voids, cracks, or breakage during drying. For this reason, all pressure sensors and screw speed control systems are regularly calibrated to ensure absolute stability before the soap proceeds to the next stage. After the vacuum extrusion stage, the dense and uniform soap mass is continuously pushed through the die head, forming long bars with either circular or rectangular cross-sections. To ensure that each bar meets the exact standard dimensions required for stamping, they are conveyed to an automatic cutting machine. Here, rotating blades slice the soap bars to a pre-programmed length. An optical sensor system continuously monitors the position and movement speed of the soap bars, synchronizing the cutting blades with the extrusion rate. This precision is crucial. Even a slight deviation or a cut that is not perfectly perpendicular can prevent the bar from fitting properly into the stamping mold, leading to defects in later stages. Each cut piece is randomly inspected for weight, squareness, and surface flatness. Products that fail to meet the standards are collected and returned to the mixing stage for reprocessing, ensuring optimal material utilization and consistent quality throughout the entire production line. When the soap bars emerge from the vacuum plotter, they form continuous strips that must be divided into smaller sections before being placed into molds. This step is carried out using either automatic or semi-manual cutting systems, depending on the production scale. In industrial lines, high-speed rotating blades are fully synchronized with the extrusion rate, ensuring that each soap segment has precise length and weight. In smaller workshops, operators may use mechanical cutters controlled by a foot pedal, a solution that still ensures accuracy while allowing better control over the cut surface. Immediately after cutting, the soap billets are pushed into metal molds by a pneumatic piston inside a hydraulic stamping machine. The powerful compression force from the hydraulic system tightly compacts the soap mass, eliminating internal voids and shaping the surface according to the mold design. This is a crucial transformation step, turning freshly cut segments into solid, uniform blanks, ready for the final shaping stage and brand logo stamping. When the freshly stamped soap bars are still soft, they move to the logo engraving stage, the step that creates a distinct brand identity for each product. Depending on the scale of production, this process may be carried out automatically using a logo stamping machine or manually with handheld molds. In large industrial production lines, steel dies engraved in relief or intaglio are lightly heated and then pressed onto the soap surface using a pneumatic piston, producing sharp and consistent imprints. In smaller artisanal workshops, craftsmen use handheld brass or steel stamps, pressing them directly onto the soap bars with controlled force. This method creates subtly unique products. Each bar may vary slightly, yet all carry a refined individuality and characteristic handcrafted value. After logo engraving, the soap bars undergo careful inspection through an optical camera system combined with manual evaluation. Technicians assess the depth and sharpness of the logo, while also checking surface smoothness, color consistency, and gloss, to ensure that every product meets aesthetic and quality standards before moving on to the final finishing stages. Products that meet quality standards are transferred to the final sorting and packaging line, ready to enter the market. After passing inspection, the finished soap bars move into the automated packaging system. Before wrapping, they are gently cooled with a stream of dry air to stabilize their structure and preserve their fragrance. Next, each bar passes through a wrapping machine using film or waxed paper, where the packaging is heat-sealed at a controlled temperature to ensure a tight seal without deforming the product. Depending on brand positioning, the packaging may consist of craft paper, branded printed paper, or transparent BOP film. All packages are automatically cut, labeled, and printed with batch codes, production dates, and origin information. The packaged soap bars are then placed into moisture-resistant carton trays, sealed with inspection labels, and transferred to storage for shipment. This final stage completes the entire production line, the moment each soap bar leaves the factory in its finished form, ready to reach consumers. Have you ever wondered why there is only a queen bee and never a king bee? The answer lies in the unique survival mechanism of bees, shaped through tens of millions of years of evolution. Each bee colony has only a single queen, the only female responsible for reproduction, and thousands of worker bees, female bees that are sterile, yet possess a special biological mechanism allowing them to secrete a white, nutrient-rich substance that sustains the queen and determines which individual will become the next queen. While worker bees live only a few months, the queen can survive for up to 7 years, 30 to 50 times longer, leading royal jelly to be speculated and celebrated as a key to longevity. In reality, royal jelly is indeed nutrient-rich, containing specific proteins, the rare fatty acid 10-HDA, and concentrated B vitamins, associated with biological effects related to anti-aging and hormonal balance, making it especially popular in high-end beauty and healthcare. However, the gap between its actual biological value and its portrayal as a miracle cure remains a major point of debate within the scientific community. If China is the factory producing over 90% of the world's royal jelly, Japan is the market that sets the strictest quality standards. Each year, the royal jelly industry generates more than $2 billion for the nutrition and healthcare market. For 1 kilogram of high-grade royal jelly, prices can range from $200 to $300 depending on standards and origin. And to understand how this miracle elixir is created in the real world, let's now head to specialized bee farms, the starting point of this entire fascinating journey. A standard bee colony can reach a population of up to 60,000 individuals. living in wooden hives arranged in clusters and operating as a living ecosystem, where all activities are tightly synchronized with the species' natural biological rhythm. To bring a bee colony into royal jelly production, beekeepers must first activate the logistics force, young worker bees. This is the only group capable of secreting royal jelly, nourished with a diet of pollen mixed with honey, containing approximately 20 to 30% protein, which directly stimulates the development of the hypopharyngeal glands responsible for jelly production. As natural floral resources fluctuate seasonally, the diet is further supplemented with finely ground plant-based protein to maintain stable jelly secretion throughout the production cycle. During this phase, beekeepers are required to frequently monitor the colony by lifting frames out of the hive. Smoke from dried leaves or sawdust is used to create the illusion of a fire, distracting the bees and forcing them to temporarily suspend defensive responses in order to focus on consuming honey. Each hive opening thus becomes a brief negotiation, demanding absolute finesse and precision, unless one is prepared to immediately pay the price with a few stings. Naturally, specialized protective armor is indispensable, as even the most experienced beekeepers are never permitted to be complacent when facing a colony in a heightened state of alert. Only when the population reaches peak condition in numbers, nutrition, and behavioral stability is the foundation for queen rearing truly complete. From this point onward, all resources are channeled toward a single individual, and the process of selecting the queen officially begins. The next step, and also the most critical stage of the entire process, is creating a queenless condition. Beekeepers typically remove the queen from the colony, mark her, and keep her separately in a protective cage for control. The absence of the queen immediately triggers the colony's survival response, forcing worker bees to prepare for the rise of a new queen. This is the golden moment that initiates the royal jelly production cycle. In nature, when a bee colony becomes queenless, worker bees select young female larvae and secrete royal jelly to nourish these potential candidates, ultimately choosing only a single larva to become the new queen. This decisive stage lasts for up to 72 hours. The selected larva continues to feed on royal jelly for life, while the remaining larvae are deprived of royal jelly, switch to consuming honey and pollen, and develop into worker bees. It is precisely this brief 72-hour biological window that humans have leveraged to create a controlled royal jelly production process, beginning at the larval grafting stage. Worker bees no longer need to select larvae themselves, as this process has already been intervened and directed by humans. Only honeybee larvae that are 1 to 2 days old, still extremely small and curved at the bottom of regular brood cells, are selected because this is the stage at which the bee's developmental pathway can still be altered. Beekeepers use a specialized grafting tool with a soft, flat plastic tip to gently lift the larva along with the thin layer of surrounding jelly, avoiding damage to its fragile body. The larva is then placed into an artificial queen cup, small cups molded from beeswax or food-grade plastic that precisely replicate the shape of natural queen cells. Once larval grafting is completed, hundreds of queen cups are placed into the hive simultaneously, forcing worker bees to secrete royal jelly at a high intensity to feed all the larvae inside and quickly identify a new queen. This stage is when worker bees produce the greatest amount of royal jelly, with the thickest consistency and the highest concentration of active compounds. If left longer, the larvae begin to grow rapidly and consume the jelly, causing both the quantity and quality of the royal jelly to decline. After the 72-hour golden window, the harvesting process officially begins. The queen cups are removed from the hive and thoroughly cleaned to eliminate debris, pollen, or excess wax on the surface. Beekeepers begin the harvest by cutting the caps of the queen cups, an operation that may appear simple but directly determines the quality of the final product. A thin, sharp, and sterilized blade is drawn horizontally across the rim of each cup, making a decisive cut that touches only the thin wax layer on top, just enough to open the cup without disturbing the royal jelly inside. A single cut made too deeply can mix wax into the jelly, disrupt its natural structure, and immediately reduce its quality. In large-scale production, any cups contaminated with wax must be completely discarded. For this reason, the process demands a steady hand, precise control of force, and years of experience, where every movement allows no margin for error. Next, the larvae are gently removed from the queen cups using fine tweezers, with movements that must be fast, precise, and controlled to preserve the layer of royal jelly beneath. At this stage, the larvae are extremely small, soft-bodied, and fully immersed in the jelly, meaning that even a slight hesitation or misalignment can disrupt the jelly's structure or introduce contamination. For experienced beekeepers, this step demands near total concentration, as each cup contains only a tiny amount of royal jelly and allows no margin for error. To obtain 1 kilogram of royal jelly, at least 2,000 queen cups must be processed, which also means that the same number of larvae are removed from the developmental cycle. This reality raises an inevitable question: is this process inhumane? In nature, worker bees also continuously create and eliminate surplus queen cells in order to select a single queen. Human intervention merely controls the timing and scale of this process, rather than introducing a new biological behavior. Moreover, these larvae are not discarded. They are often repurposed as protein-rich food, used as ingredients in high-grade animal feed, or consumed in certain Asian markets, helping reduce biological waste and complete the value cycle of royal jelly production. Meanwhile, the thick, milky white substance settled at the bottom of each queen cup is royal jelly, a rare biological essence produced to nourish the queen of the hive. The jelly is extracted directly using specialized spoons or suction tools, with slow but decisive movements to minimize exposure to air, light, and heat, as even slight deviations can reduce its biological activity. For experienced beekeepers, this step demands near absolute concentration. Each queen cup yields only a few drops of jelly, and any mistake is irreversible. Royal jelly is expensive, not only because it is difficult to harvest, but also due to its unique nutritional profile. Specific proteins, the rare fatty acid 10-HDA scarcely found elsewhere in nature, concentrated B-complex vitamins, and numerous bioactive compounds that are still not fully understood. It is this combination of exceptional biological value, extremely low yield, and a highly labor-intensive process that makes royal jelly one of the most luxurious substances derived from nature. After a harvest cycle is completed, beekeepers graft new larvae and return the queen cups to the hive, beginning the next 72-hour cycle. This process can be repeated multiple times, but only takes place during the peak flowering season, when the colony is at its strongest. At the same time, strict limits are always observed. Colonies are rotated, the number of consecutive cycles is restricted, and bees are allowed to rest outside the flowering season. If these biological thresholds are exceeded, the colony will quickly weaken, something no professional beekeeper would ever allow. And when the flowering season comes to an end, tons of fresh royal jelly are collected, cold stored, and rapidly transported to modern facilities, where they are processed into dietary supplements in the form of capsules, powders, or concentrated liquids. At the factory, the processing begins as freshly delivered royal jelly is fed directly into a freeze-drying system, the most critical stage of the entire process. Here, water is removed from the royal jelly through sublimation under low temperature and vacuum conditions, allowing enzymes, specific proteins, and the fatty acid 10-HDA to remain largely intact. The result is a dry royal jelly powder that is biologically stable and suitable for long-term storage. Only after this step is the royal jelly powder transferred into sealed stainless steel mixing tanks, where it is blended with food-grade excipients in carefully controlled ratios to stabilize the structure, ensure proper binding, and prepare the material for tablet formation. The blended powder is then fed into a high-pressure tablet press, where compression forces reaching tens of megapascals transform the fine powder into tablets that are uniform in size, weight, and hardness, leaving behind the fragile original form and becoming a stable product that can be precisely controlled and accurately dosed. Before packaging, all tablets undergo strict screening. Any deviation in shape, weight, or surface quality is removed, and only tablets that meet quality standards are retained. Finally, the product enters an automated packaging line, where it is sealed into blister packs or containers, ready to leave the factory and enter the global supply chain. Pure royal jelly is neither sweet nor aromatic. It has a sharp, acidic taste and is difficult to consume, especially for older adults. For this reason, royal jelly tablets provide a key solution, transforming a biologically powerful but challenging raw material into a stable, convenient product with precise dosage control, bringing the essence of the queen bee closer to people around the world. As soon as the freshly harvested apples arrive at the processing plant, they are gathered in the raw material receiving area and quickly placed into temporary cold storage to preserve their natural freshness, crispness, and flavor before processing. For premium apples intended for fresh consumption, every batch must undergo a rigorous inspection by quality control specialists to ensure compliance with strict standards of appearance, uniformity, and food safety. Once the inspection process is complete, the qualified batches of apples are transferred to the processing line, beginning with a step that seems simple but is absolutely essential: washing. At the start of the process, apples are emptied into large circulating water tanks, maintained at an ideal temperature of 20 to 25 degrees Celsius, combined with continuous air bubbling and a diluted chlorine solution at a safe concentration. This soaking stage not only removes dust, soil, and surface bacteria, but also eliminates pesticide residues that may remain from cultivation and transport. The cleaning doesn't stop there. After soaking, the apples move through soft roller conveyors, sprayed with high-pressure water jets from multiple angles, thoroughly cleansing every crevice of the peel without scratching or dulling its natural shine. After being thoroughly washed and polished, thousands of gleaming apples move onto soft bristle roller conveyors, equipped with high-capacity air blowers that gently remove residual moisture from their surface. This step helps prevent mold growth and spoilage during subsequent stages of processing. The conveyor then carries the apples to a manual inspection station, where trained workers carefully visually examine each fruit, removing any that are bruised, scratched, or misshapen. This ensures that only the most flawless apples proceed to the next stage, the automated optical grading system, where precision technology takes over. And now comes the most precise and crucial stage of the entire process: apple grading using an automated optical sorting system, a technological breakthrough that reduces manual errors by up to 90% and determines the destiny of every single apple. The entire operation takes place on a smart conveyor system, equipped with color sensors, weight detectors, and high-resolution cameras. The system can identify size, gloss, tone, and even the smallest imperfections such as bruises, cracks, or discoloration, details that the human eye can hardly detect with precision and consistency. Apples that fail to meet standards are automatically removed by ultra-precise air jets, while those that pass are classified according to size, quality, and intended use. Apples with a beautiful shape, even color, and flawless skin are sent to the fresh apple packaging line. Here they are arranged into trays or packed into plastic bags, then sealed securely and labeled with full product information. Finally, the finished products are placed into cartons, stacked on pallets, and moved to cold storage, awaiting distribution to consumers worldwide. While the most flawless apples have already made their way to consumers around the world, the journey continues at processing plants dedicated to apple juice and cider production. Each day, a large-scale facility, such as Mott's, USA, can receive thousands of tons of apples from farms across the region. Unlike table apples, processing apples don't need to look perfect, but they must meet strict standards for sweetness, crispness, and flavor to produce a pure, well-balanced juice. After being received, washed, and quality checked, the apples are fed into high-capacity grinding machines, equipped with high-speed rotating blades, capable of processing hundreds of tons per day. Under intense centrifugal force, the apples are crushed into a fine mash of pulp, juice, and peel, creating the apple mash, the essential raw material for the juice extraction stage that follows. The crushed apple mash is transferred to the pressing stage to extract its precious juice. In traditional or medium-scale factories, the drum press, a long-standing reliable technology, remains in use thanks to its simple design, durability, and ease of maintenance. However, the belt press has become the modern standard, favored by large industrial facilities for its ability to operate continuously, deliver superior throughput, achieve high juice recovery rates, and preserve the natural flavor of the apples. Each day, an industrial belt press system can process hundreds of tons of apples, achieving productivity 2 to 3 times higher than conventional presses. Under immense pressure, the juice is separated and flows through fine filtration screens, while the remaining dry pulp is collected separately. In modern factories, apple pomace is not wasted, but dried or pelletized for efficient reuse. Rich in fiber and nutrients, it is used as a natural livestock feed or biologically fermented to produce organic fertilizers. It also serves as a sustainable raw material for the green industry, processed into pectin, ethanol, pharmaceuticals, and natural cosmetics, maximizing the value chain of every harvested apple. The juice obtained after pressing is sent to the filtration stage, a crucial step that removes pulp, pectin, and impurities, ensuring clarity and natural flavor. Various filtration methods are used today, from traditional mesh filters to microfiltration and advanced tubular membrane systems. At this point, the process diverges into 2 distinct directions. For apple juice, the filtered liquid is transferred to heated mixing tanks to stabilize enzymes and improve clarity. This process occurs at 35 to 45 degrees Celsius for at least 30 minutes, allowing the breakdown of pectin and remaining colloidal compounds. The juice is then rapidly cooled to stop enzymatic activity before entering a tubular sterilization system, where it is quickly heated to 85 to 90 degrees Celsius and immediately cooled, ensuring microbial safety while preserving its natural freshness and flavor. In the production of apple cider, the filtered apple juice is transferred to the fermentation area, the most crucial stage in transforming fruit juice into alcoholic cider. Depending on the scale of the facility, each fermentation tank can hold anywhere from several hundred to tens of thousands of liters of liquid. Once yeast is added to the filtered juice, the fermentation process begins, lasting from 5 to 14 days under strictly controlled temperatures. After the yeast completes fermentation, the sediment settles at the bottom of the tank. At this stage, the clear cider is siphoned off and transferred to the aging phase. Depending on the type of product and the techniques used by each facility, the cider can be aged in large stainless steel tanks or traditional oak barrels. Aging in stainless steel tanks preserves the cider's fresh, crisp apple character, while aging in oak barrels allows it to absorb woody aromas, tannins, and natural compounds from the barrel walls, creating a richer, deeper flavor with a long, smooth finish. The aging period typically lasts from 1 to 6 months, and for premium ciders, it may extend up to a year. Throughout this time, technicians regularly take samples to monitor key indicators such as clarity, alcohol content, acidity, and microbial stability. Once the cider reaches the desired quality standards, it is passed through a fine filtration system to remove any remaining sediments, yeast residues, or impurities. Before bottling, both apple cider and juice must undergo rigorous quality control tests in the laboratory. Only batches that meet all specifications are approved for packaging. When everything is ready, the bottling process officially begins, the final stage that completes the entire production journey and delivers the product to consumers. First, empty bottles are sent through a specialized cleaning system, where they are thoroughly washed with sterilized water or high-pressure air at 70 to 80 degrees Celsius to eliminate microorganisms and remove any dust or residue. After drying, the bottles are automatically transferred to the filling section. Here, the automated filling system operates with near-perfect precision. Once filled, the bottles move on to the automatic capping unit. Caps, whether screw, press fit, or aluminum, are sealed tightly under controlled pressure to guarantee airtight closure, prevent oxidation, and preserve the product's natural flavor. The sealed bottles are then sterilized and dried before proceeding to the labeling section. Each label clearly displays the brand, origin, production date, expiration date, and traceability code. After a final quality check, the finished bottles are packed into plastic crates or cartons, stacked on pallets, and transferred to cold storage, ready for distribution to markets and consumers around the world. Today, most cocoa is fermented in multi-tier wooden boxes that allow even turning and better temperature control. The ideal temperature throughout fermentation must stay between 40 to 50 degrees Celsius, with the bean mass kept aerated and not overly moist to avoid anaerobic fermentation. Crucially, the beans are turned once a day from the second or third day onward, a vital step to distribute heat and oxygen. Just one mistake, such as delayed turning or excess water, can leave an entire batch overly acidic, off-flavored, and severely downgraded. This is an irreplaceable link in the journey that transforms raw, sharp-tasting, fruit-scented cacao into premium chocolate. After 5 to 7 days of fermentation, when the beans have turned dark brown and release a characteristic cocoa aroma, the wet beans are brought out to dry under the sun for up to 7 days. This is a crucial step that reduces moisture from over 60% to around 7%, meeting storage and export standards. Farmers usually dry the beans directly on concrete yards or bamboo mats. In some areas, raised drying racks with roofs are used to avoid sudden rain. This stage also demands precision. The beans must receive enough sunlight each day, be stirred constantly to dry evenly, and kept free from moisture or mold. Just one damp spot can ruin an entire batch of cocoa. Once the cocoa beans reach the proper dryness level, they are sorted to remove impurities, flat beans, and low-quality fragments before being bagged and stored. After receiving confirmation from buyers or collectors, the entire batch is transported to the export port, ready to set off abroad, heading toward a dazzling world of precision machinery and polished production lines, the chocolate factory. Now, let's step into the most anticipated part, the chocolate production paradise of the world's most developed countries, where modern production lines dominate this billion-dollar industry. At the factory, cocoa beans, once received, must undergo a quality inspection before officially entering the chocolate-making process. a step that seems simple, yet is absolutely non-negotiable. After passing inspection, the qualified batches are sent straight to the cleaning area. Workers slice open the bags, pour the beans into the feeding hopper, and send each cocoa bean one step closer to its mission of becoming chocolate. And when everything is finally in place, the most crucial step to unlock the cocoa's true flavor begins: roasting. At bean-to-bar facilities or small-scale workshops, the most common choice is paddle-style roasters. Inside is a semi-closed roasting chamber where rotating paddles constantly toss the beans to ensure even heat exposure. This type of machine allows direct observation of the bean's color, aroma, and sound throughout the roast, while offering flexible temperature control from 100 to 140 degrees Celsius, adjusted in small increments with just a few buttons. The paddle speed can also be fine-tuned to suit different roasting styles, a major advantage for small batches requiring precise manual adjustments. In industrial factories, drum roasters with capacities of hundreds of kilos per batch are the optimal choice. After the beans are roasted, they move on to the next step, separating the shells to obtain the cocoa nibs. Large capacity winnowing machines can process hundreds of kilos of beans per hour, operating on the principle of cracking the beans and then using strong air currents to blow away the lighter shells while retaining the heavier nibs. A multi-stage sieving system further sorts the nibs by size, ensuring that only those meeting the required standards move on to the next stage. The next step takes the freshly separated nibs into the grinding system to create cacao mass, the foundation of the entire chocolate industry. First, the nibs are coarse ground using roller crushers to break down their structure and release the natural cocoa butter, gradually turning the mixture from solid particles into a thick paste. The mixture then moves into ball mills or granite stone grinders for deeper refinement, reducing particle size to just 15 to 30 microns. Heat generated from friction melts the cocoa butter, transforming the mass into a smooth, homogeneous cocoa liquor, the core ingredient that determines the silkiness, richness, and flavor profile of the final chocolate. A portion of the cacao mass is fed into a massive hydraulic press to separate the cocoa butter. Under tons of pressure, the melted cocoa butter flows out in a steady stream, while the dry cocoa cake is pushed aside to be ground into powder. A fun fact: chocolate melts in your mouth, but not in your hand, and cocoa butter is the secret behind that. The dry cocoa cake is then fed into a specialized grinding system to produce cocoa powder. High-speed grinders break the solid cake into fine particles, resulting in a light, fluffy cocoa powder with a rich aroma, an essential ingredient in confectionery, beverages, and chocolate production. And once all the core ingredients, cocoa mass, sugar, and cocoa butter, are ready, they are poured into an industrial mixer for blending, the opening step that defines the structure and flavor of the chocolate. First, the cocoa mass is stirred and warmed. Then, sugar and cocoa butter are added in sequence, transforming the mixture from loose, dry particles into a thick, cohesive crumb. The mixer continues to knead and compress the blend so that sugar particles become evenly coated with fat, forming a uniform pre-chocolate base. Once it reaches the proper consistency, the mixture moves directly into the conching stage, where chocolate is refined, aerated, and polished to perfection. Conching, the most critical refinement step in chocolate making. In this stage, the chocolate mixture is continuously agitated, ground, and aerated in conch machines for anywhere from a few hours to over 72 hours, depending on the desired quality. Heat and friction drive off acidic notes, smooth out harsh flavors, and allow cocoa butter to fully coat every solid particle, creating a silky texture. The process also deepens aroma development through oxidation and the release of complex flavor compounds. The result: chocolate with its signature smoothness, shine, and refined, well-rounded flavor. When the conching process is complete, the liquid chocolate is kept warm in controlled holding tanks to maintain a stable viscosity before moving into the molding stage, the final shaping step that determines the product's appearance. In modern factories, the molding process is almost fully automated. A conveyor system carries clean polycarbonate molds through a vibrating unit, after which liquid chocolate is precisely deposited into each cavity by dosing nozzles. Immediately after filling, the molds pass through a high-frequency vibrating table to remove air bubbles and ensure the chocolate spreads evenly, preventing surface holes or cracks in the finished product. Next, the molds enter a cooling tunnel set to a precise temperature range, allowing the chocolate to solidify and contract slightly for easy demolding. Once properly cooled, the molds are inverted and gently tapped by a mechanical system so the bars or pieces of chocolate fall onto the conveyor. From here, robotic arms or automated belts transfer the pieces through inspection, wrapping, packaging, and boxing. Every step runs seamlessly, cleanly, and accurately, completing the long journey from raw cacao to glossy, finished chocolate ready for the shelf.